Section 6.4, Work. In general, if an object moves along a straight line with position function s of t, then the force F on the object in the same direction is given by Newton's second law of motion as the product of its mass m and its acceleration a. So force equals mass times acceleration, and remember acceleration is the second derivative of position. In the case of constant acceleration, the force F is also constant, and the work done is defined to be the product of the force F and the distance d that the object moves. So work is defined to be force times distance. Let's do an example. How much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high? Use the fact that the acceleration due to gravity is g equals 9.8 meters per second squared. So we first have to figure out what our force is, and then we can figure out what the work is. So force equals mass times acceleration. In this case, the acceleration is due to gravity, so it's mass times g, which is 1.2 that we were given, because the book is 1.2 kilograms. Gravity is acting at 9.8 meters per second squared, so multiply by 9.8, and we get 11.76 newtons. So now we can calculate the work. Work is force times distance, so that's 11.76 newtons that we calculated, times 0.7 meters. So that's 8.2 Newton meters, but we can use joules instead of Newton meters, where 1 joule is 1 Newton meter. How much work is done in lifting a 20-pound weight 6 feet off the ground? Well, in this case, we have a 20-pound weight, so we don't have a mass. We have the force. So we can just go straight to the work equation. Work equals force times distance. So that's 20-pound force times 6-foot distance. So that's 120 foot-pounds. So we didn't have to calculate the force ourselves in this case. We didn't have to multiply by gravity, because instead of getting a mass, we were given a weight, which is already a force and not the mass of the object. If the force f of x on an object is variable, then we define the work done in moving the object from A to B as the limit of the sum of the force times distance values. So basically, what we do is we have force like some function, variable, and we would like to know what the work done is, so we have to multiply it by distance, but it's different at every single point. So we can't just multiply a single constant force. So what we do is we multiply the force over here by some tiny little distance, delta x, and then we multiply the force over here and the force over here, and we get the force done from here to here, from A to B, by taking the limit as these little rectangles for force and distance become arbitrarily small. So let's do an example of that. When a particle is located a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done in moving it from x equals 1 to x equals 3? Well, the work done is just the limit of this Riemann sum, so that means it just becomes an integral by definition. So it's the integral from x equals 1 to x equals 3. And then we integrate our force times distance, so the force function is x squared plus 2x, and our distance will be a tiny little dx. When we add up all of these little dx's from 1 to 3, then we'll get the total distance. So we do our antiderivative. We get x cubed over 3 plus x squared, all from 1 to 3. And that becomes 50 over 3. So that's the work done. So the work done is 16 and 2/3, and it's foot-pounds. We're not always given the force equation though. In fact, more often than not, we have to calculate it ourselves. So we can do that using a few different techniques, one of which is Hooke's law. The force required to maintain a spring at stretched x units beyond its natural length is proportional to x. So that means that we can write it as f of x equals kx, where k is a positive constant called the spring constant. So looking at our figure, we can see that here's a spring in natural position, and then you stretch the spring outward, and the force acting on it at any particular stretched value, x, is f of x, which we can write as kx. So here, now we have one way to calculate the force that we're going to use for our integrals, provided that it models motion in this sense. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? Well, first, let's figure out how much it stretches from 10 to 15. So from 10 centimeters to 15 centimeters, well, that means that it's stretched 5 centimeters, which is 0.05 meters. We want to write it as meters because we want our answer to be in joules, which is Newton meters. So this is how much it's stretched at the 40 newtons that they gave us. Because they said 40 newtons is required to stretch it this much, so that means 40 meters. So 40 newtons is required to stretch it 0.05 meters. So that means that over here at 0 would be 10 centimeters, and then over here is 15. So it's stretched 5 in our particular example. Okay, so that means that at 0.05 meters it's stretched to 40 newtons. So if we write our force as a function, the force at 0.05 meters must be equal to 40 newtons. So f of 0.05 must be equal to 40. And we're going to use Hooke's law. So we say that that's where f of x must be equal to some constant k times x by Hooke's law. So let's see if we could solve for this constant k. Well, now we know that 0.05 times k must be equal to 40. So that means that k must be equal to 40 divided by 0.05, which is 800. So now we have our equation for f of x. F of x, instead of equaling kx, must equal 800x. So now we can calculate the work done. Our work done be our integral. Let's see, we want to do it for stretching the spring from 15 centimeters to 18 centimeters. So that means that we're going even farther. We want to go from 15 centimeters to 18 centimeters. So that means that, remember, our force is a measure of how much we've stretched. So at 15 centimeters, we've stretched 5. At 18 centimeters, we've stretched even more. We've stretched 8, because we stretched 3 more. So that means that our integrating has to happen from 0.05 to 0.08, because we integrated how much we've stretched. So we integrate our function, our force function, 800x times our distance, dx, and we get 800 x squared over 2, evaluated from 0.05 to 0.08, and that becomes 400 times 0.08 squared minus 0.05 squared, which is 1.56 joules. Okay, say a 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. Let's see how much work is required to lift the cable to the top of the building. In this case, we cannot use Hooke's law. We'll have to figure out an equation for the force ourselves. We're told that 200 pounds is for the cable, and that's for every 100 feet. So that's the same as saying it's 2 pounds per foot. So what we can do is we can take that 2 pounds per foot and we can multiply it by feet or by some distance, and then we'll have just the pounds, the weight. So let's see if we can do that. How about we draw this a little bit? Let's say here's the building. Not such a great building. Let's put an axis over here. So here's my axis. Here's 0 at the top of the building. The cable extends downward. How about we look at it at a particular x value? Let's say xi star, some sample point. So at that sample point, I'm going to cut the rope up into a tiny little piece. It'll be 2 pounds times whatever feet they are at that little piece. I'll call that little distance in the rope delta x. So when I multiply that together, I'll just have the force. So, oh, by the way, the end of this is at 100. So let's take 2 pounds per foot and multiply that by delta x, and that'll be our force. We do this along the entire rope, chopping it up into little pieces. We take the limit as these lengths of these little pieces goes smaller and smaller and smaller as we do more and more and more pieces. And we multiply this by our distance. Notice the distance from here to here to move that piece is just the x value that we chose to be our sample point. So that means our distance that we have to multiply by is xi star. So that means that 2xi star times delta x is the amount of work needed to move this tiny little piece over here. So if I add up the next amount of work for the next piece, or the previous piece, and the next piece, and the next piece, I add up all of those little work amounts for all of those arbitrary little pieces of cable, then I'll have the work done to lift the cable to the top of the building all the way. Okay, so we get work equals the limit as n goes to infinity of the sum from I equals 1 to n of 2xi star delta x. So that's just the integral from 0 to 100 of 2x dx, which is an easy integral. We just get x squared from 0 to 100. So that's just 10,000 foot-pounds. So you can see that in order to build any of these integrals, you have to first figure out the force and the distance, multiply the two of those for an arbitrary piece. This is for one little piece. That means that if I wanted to lift this tiny little section of rope, just this section on its own, it would require this much work. But I wanted to know how much it would require for this entire thing. I can't do the whole thing at once because all of these pieces are at different distances, and they all have different amounts of force to xi star. So I need to construct one arbitrary piece and then integrate to accommodate for the way that it's changing along the rope. It should make sense that it requires different amount of force. Obviously, moving this piece up is going to require a lot less force than a lot less work than this piece, all the way at the bottom. So in order to accommodate for that, we keep everything general and then integrate at the end. Say a tank has the shape of an inverted circular cone with height 10 meters and base radius 4 meters. It is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all of the water to the top of the tank. The density of water is 1,000 kilograms per meter. Okay, let's see if we can draw this. Okay, that's roughly cone-shaped. We are supposed to have a base radius of 4 meters, so let's put that in. So that's 4 meter base radius. Well, how about we go down the tank, but first we should probably draw a water level somewhere. So we're filling this with water. So how about it's filled up, let's say, to a height of 8 meters. So let's see if I can draw a 2 meter difference. Okay, so if this thing's filled up to a height of 8 meters, then that means that the water is 2 meters away from the top. The total height of the tank is 10 meters. Almost forgot my meters. And if I want, I can put an axis that goes down into this thing. So how about that's at 0? And then make this an x-axis. It goes down deeper and deeper and deeper into the water. So now it's behind the water, inside of it, and it comes out at the bottom. And that's our x-axis now. So we would like to know the amount of work done to pump all of this water out, but the amount of work done is going to be different depending on what level of water we're at. The work will be a lot more to pump out certain parts depending on where the water is and how much water it has to pump out at that level. So I want to know how much work it's going to be to pump out, let's say, an arbitrary little section of water. So I can do that by drawing a disk. So let's say I want to know how much work is done by pumping out just this one disk of water. So this disk has a tiny little thickness delta x. It also has some sort of radius. So let's see if I can draw. This is the radius. We'll call that r. However, I want to be able to sum up over all of these little disks, so I need an index, so I'll call it ri. So this will be the ith radius on the ith disk. And there's tons of little disks that make up this water that's all being pumped out. We're going to find the work done on a single one of them in terms of x, and that way we can integrate over the entire thing. So in order to figure out what this ri is, because obviously we can't sum up over ri, we have to sum up over x or xi's. Well, if this is ri, that happens at some sample point xi. So we'll call this xi star for our sample point. And that's going to be at the level that the disk is at. So if this whole thing is 10, and from here to here is xi star, then that means that this is 10 minus xi star for the remaining distance after the disk. I didn't line that up very well, but you get the general idea. Okay, I think we're even closer now to eliminating Ri. We could take this triangle over here. We know that from here to here is a triangle, from here to here is a triangle, so we could probably use some similar triangles. So let's try drawing that triangle separately. And let's draw Ri. I think it was a little bit lower. Doesn't really matter. Okay, so we know that the top of the triangle is this part right over there. So it has a length of 4. We know that the bottom part of the triangle over here is this bottom part over here, which is 10 minus xi star. And we know that the entire height of the triangle is the entire height, which is 10 meters. So that means that if I take r and I divide it by 10 minus xi star, that should be the same as taking 4 and dividing it by 10. So we can write Ri over 10 minus xi star must be equal to 4 over 10, which we can use to solve for Ri and eliminate it. So Ri must be 2/5 times 10 minus xi star. So now we can get the volume of one of those disks. Remember that force is mass times acceleration. So if I can figure out what the volume is, they told me the density of water. Density is mass over volume. So if I take density, I multiply it by volume, I'll get the mass. If I get the mass, I can get the force. If I get the force, I can get the work, and I can finally do my integral. So we take the volume, which is going to be pi r squared, so pi ri squared for us, times delta x, because it's the area of the face of the disk times the height of the disk, the little thickness. So that's 4 pi over 25 times 10 minus xi star squared delta x. So our mass for a particular disk, for the ith disk, is density times volume, which is about 1,000 times 4 pi over 25 times 10 minus xi star squared delta x. So we could simplify that a little bit. We get 160 pi times 10 minus xi star squared delta x. So now we finally have our mass. We can calculate force. Remember that force is our mass times acceleration. In this case, acceleration is due to gravity. So that's going to be approximately 9.8 for the gravity, times our mass that we calculated, which is 160 pi times 10 minus xi star squared. delta x. So that becomes 1568 pi times 10 minus xi star squared delta x. Okay, we finally figured out the force. We can figure out the work now by taking force and multiplying it by distance. So the force Fi times the distance, well, the distance from the top to the disk is just xi star. That's how far along we travel along our x-axis that we put in the middle. So this will be Fi times distance xi star. So all we have to do is just throw an extra xi star in there. So let's do that. 1568 pi times an extra xi star times 10 minus xi star squared delta x. Now that we have the work done for a single disk, we can stack up all of the disks inside of this thing to get the work done to move all of the water. So we write the work, total work, as the limit, as n goes to infinity, of the sum from I equals 1 to n of 1568 pi xi star times 10 minus xi star squared delta x. So that's just the integral from where our water starts, which is at 2, all the way to the end at 10. So we go from 2 to 10 of 1568 pi x 10 minus x squared dx. It's not too bad of an integral. We can take out the 1568 pi. We're just left with the integral from 2 to 10 of the inside. 10 minus x squared times x becomes 100x minus 20x squared plus x cubed. So we do our antiderivative. We get 1568 pi times 50x squared minus 20x cubed over 3 plus x to the 4th over 4, all evaluated from 2 to 10. So we do our math. We get 1568 pi times 2048 over 3, which is approximately 3.4 times 10 to the 6 joules.